Okay, hello everyone. Nice to see you again. Let's continue with the computational methods in engineering. So this class, we're going to just follow up regarding the interpolation and curve fitting, especially on the higher orders of polynomial curve fitting, and then talk about the curve fitting tools that are available in MATLAB. And then we'll specifically talk about how we can solve equations. Because in engineering, most of the time it's about solving equations, right? It can be single equation, it can be system of equation, so on and so forth. So let's do a quick recap of last class. Last class, we talked about interpolation in the beginning. So again, we should pay attention that interpolation is assuming that all of the data points we collected are real. And we're trying to find out the data that at location that we didn't measure, right? So then there can be linear interpolation, cubic spline interpolation, so on and so forth. And then we talk about curve fitting. So the idea for the curve fitting is that we assume that the data we collected are not accurate, right? So there's a major difference. The interpolation assumes that data are accurate, and curve fitting assumes that data are not accurate. It's subject to uncertainty. So that's why we want to conduct a regression, so sort of to find out the trend line for all of the data. And then we can use this trend line to predict the data at location or at points that have not been measured. Okay, so specifically on curve fitting, we talk about the linear regression. Okay, so basically linear regression is just first order regression, right? So we assume that there's a line that can sort of pass through all of the different data points. And then we can basically reduce the mean square error and then try to predict the trend line for all of the data. So then we could also assume that there are higher orders of lines that can represent the data, right? So basically straight lines are not only equation that could be analyzed with the regression technique. So we know that the Taylor series, right? Taylor's theorem tells us that any smooth function can be approximated as a polynomial. So a common approach is to fit the data with a higher polynomial in this form here. Okay, so it can be a1 to the x multiplied by x to the power n, a2 x to the power n minus 1, so on and so forth, right? So then we can just check how the higher order of polynomial fitting can help represent the data. Okay, so let's create a new script. Let's bring this script to the MATLAB, or let's just use this way. Okay, we can just type in this way. Then let's create something with class 15. So let's name this as 15. Just call it new because I already have this file here. Okay, so the first one, higher order of regression. Okay, so then let's define our x and y again. So this is our x and y data. X equals 0, 5, separate by 1, and y is 15 and 9, 6, 2, 0. Okay, so we can do a quick plot of x and y. So this is the data that we have been showing for our last class. So this is the data. So we said that we could do a first order polynomial, first order fit or the linear fit to find out the line that connects everything, or not connecting everything, but represent the data. Okay, so so the way we do that is just do polyfit. We fit x and y, and then with the order of 1, right? So we said that if we do polyfit, then it's going to return you the basically the slope and the intercept. Okay, so then the thing is, how do we show this data here? So we could basically do, let's say we create another stream of data, right? So let's say separate by 0.1 until 5, and then let's say y x new, y new, x multiplied by minus 2.9143 plus 14.2857. Okay, hold on. Plot x new, y new. And let's just use line to represent the data. Okay, this is not showing up. Let's see what's the error. So the vectors must be of the same length, which means that here we need to do x new. Okay. All right, so this is our new data, right? So you can see that basically here is the original data, and then this is a linear fit that goes through all of the data points. Okay, so well, you see, this is, I would say, a pretty good fit. But the thing is that now, I mean, there are still pretty big error here, right? So the points are not getting close to the line here, which is the reason why we probably sometimes want to use a higher order polynomial to let the data fit better. Okay, so how to do that? We can just use this term here and change it to 2. Okay, so instead of using 1, we change it to 2. So we can do, let's just comment here. So the number after x and y indicates order, right? The order of the polynomial. So we can run this, right? So now you see that in terms of the result here, it's showing you 3 parameters. And actually the 3 parameters here represents the number in front of the second order, because now it involves second order, right? So n should be 2, 1, and 0. So then it's going to be A1, A2, and A3. So actually these are A1, A2, and A3. So then what we do is we can just copy this term here, right? 14.4 something. And then use a higher order term here. Multiply by x new to the power of 2. So we have to use a dot here because x is an array here, right? So x new and y new. Now you have all of the data here, and then you see how this higher order of fitting is going to tilt the result here, right? So the original line is a red line, that's a linear fit, and you can see that the higher order fitting, right? So you start to have some of these curvature here to fit the data. Okay, so we can try even higher order of fitting, right? So we can try 3, and then to run it, now you see 4 factors. But the thing is that now to represent y new, it's going to take more efforts for us to put in all of these values here. So there's an easy way to do that, which is the polyval function. Okay, so the polyval function, in terms of the polyval function, you just need to type in, or you just need to feed the result of the polyfit and then provide the new x. Okay, so what it means is that instead of typing in these values, you can just do polyval and then type in polyfit x, y, and then which order are we talking about? 3, right? So 3, and then let's put in x new. Okay, so this is a y new. So now we don't need to have this term anymore. Okay, so let's do CLC clear. Run this function again. So now you can see this is a third order polynomial, right? You can see that the data will actually try to fit better, right? So it's trying to further reduce the error here. Right, so this is a third order polynomial. We can do fourth order polynomial. Let's just try to plot it again. Right, so you can see that fourth order polynomial is going to help us fit the data even better. So now you can even see that the curve here is now basically intercepting all of these circles for the data points. So you can see from the third order to fourth order is a pretty big improvement. You can try fifth order, right? So it's fitting the data even better. And actually, you can try it tens order. Let me see. Yeah, the tens order is going to give you some strange shapes. Okay, so let's see. Fifth order. Fifth order is still fine, right? So then this is basically the issue, because if you do tens order, basically there can be a lot of fluctuations that are not controlled. So as long as the curve can go through the data points, right, reduce the error, it's going to use that, right? So we're not evaluating the error at the points that were not measured by the data, because we only measured at these existing data points, right? And we're trying to find a polynomial curve that fits all of the data. So it could be that if you do tens order and then basically at the points that are not being measured, you can get very strong curvature here, right? So then the issue is, well, which order should we use, right? Which order of polynomial should we use? So I would say that in engineering, most of the scenario will actually just use either first order or second order, because those are, I would say, the easiest to explain based on the physics, or based on the physics or chemistry, right? So if you're telling me that some simple mechanism, some measurement has to be fit by a tenth order of polynomial, then you have to provide the background mechanisms. Basically, it's going to be layered by layered, right? So if it's tens order, then you have to consider, for example, the gradient. Why the gradient is a ninth order polynomial, or why the, let's say, the second order derivative is an eighth order. So because each of the gradient will represent some physical process, right? So because of that, I would say most of the time we're still going to use either first order, which is a linear regression, or the second order, right, which is basically the second order polynomial regression. Okay, so because of that, here I want to talk about the overfitting. I sort of showed this plot in our last class, right? So you could get a bunch of data, right? So it's totally random. You can't even fit it with a linear regression, right? But if you use the higher order polynomial, right, it could be, let's say, in tens order, you could be connecting all of the data points together, and then this is going to give you an illusion, right, of how the data or how the background mechanism looks like. Okay, so basically the overfitting is something that we want to avoid when we're trying to conduct these the curve fitting process. Okay, so this is the interpolation. So basically this is the contents of our last class. Let's just skip this slide. And then this is basically an example, right? So here we're trying to determine the water in a culvert, right? So determine how much water will flow through a culvert is not as easy as it might first see. The channel could have a non-uniform shape, right? For example, it's not a rectangular shape, because if it's a rectangular shape, then the height is going to be linear, or mostly linear, with the total flow, right? But if it's having a irregular shape, then the flow rate might be difficult to predict, right? The high, of course, we know the higher the height, the stronger the flow, right? But as you go to the lower height, right, because the cross-section area is smaller, then the flow is going to be much smaller. So a numerical approach allows us to fold all these concerns into a model of how the water actually behaves. So it wants us to compute a best fit linear, quadratic, second order, right, cubic equation for the data and plot them on the same graph. Which model best to represent the data? Linear is first order, quadratic second order, cubic is third order, and also include a linear model forced through zero, which is something we also showed in our last class, right? So then here is how we can look into this problem. So we need to first put in the data, right? So h, which is the height, 0, 1.7, 1.5, 6, 2, 4, 0.2. Flow is 0, 0.6, 3.6, 0.3. Right? So this is going to be, I would say, the data coming from hydrology, right? Civil engineering, where we try to define or try to design the best shape for the channel or for the culvert. Right? So then we can make the plot first. Plot HF with the circle, because we know that these are the actual data. Right? So let's do clear CLC. Just clean up the data that we had before. And you can see how the curve looks like, right? Of course, we know that when the H is 0, basically there's no height of the water, there's no flow. It's not going to create any flow. And as the height increases, especially when the height is really high, then you're going to also see a very high flow rate. So by just looking at this curve here, you might think, well, this could be a second order or a third order, let's say, in a third order trend, right? Because it doesn't look linear for sure, right? So then let's try to fit the data. So we said that we could do the polyval, right? The polyval. So let's define a new height, right? H new is going to be, let's say 0 separate by, let's say 0.01 separate by, until 6. Okay, so this is basically a finer separation of the height, right? So then we can do F. First order is polyval or polyfit of H and F is the first order. Okay, so then let's do 2 is this quadratic regression, 3 is a cubic regression, 2 and 3. Okay, so then we can do hold on, plot H new F1, 2, 3. Okay, so these are the different curves, I would say, right? So then we can do legend. So data, this is the original data, right? So first order, second order, and third order. And then let's add the axis title, right? X label, height, Y label, flow. All right, so to just make it more accurate, right, so we can add the units as well. So ft to the power of 3 per second. Let's just put it this way. There's an error here. So let's see, polyfit. Oh, we need to provide the x. We need to provide the x value. So let's try to display this in a better way so that we can combine our M file together with the program. So we should be layout and then default. Let's see. Remote. Here, I think there's a way for us to dock it. This is how we dock it. Okay, so we said that for the polyval, we have to provide the new height, right? These finer x-axis. Okay. All right, so this is how our fitting looks like. Okay, so you can see that this is the original data that we talked about. There's first order fit, there's second order fit, right? There's third order fit. Right? Third order basically has a better fit, right? The error, right? The least squares error is being achieved by the third order. So square error basically is the difference between our curve fitted result and the original data. Okay, so these are the 3 different orders of polynomial that tries to fit the data. So you can see that the third order actually fits better. Okay, first order, second order has a basically the fits are not as good. And the other thing, right, so you can see from this problem is that it also wants us to include a linear model that forced through zero. So what does that mean? So the thing is, we know that when the height is zero, the flow should be zero, right? But right now with our linear fit, you can see that when the height is zero, it actually has a negative flow, which means that the water is flowing backwards, right? So this doesn't make sense from the physical perspectives, right? So basically, we want to create a linear fit that goes through zero, and then it still tries to minimize the error. So for that, we talked about how to do the fit in our last class, right? So eventually the linear fit is about the matrix calculation. It's a left division method, right? It's an over-defined problem that you can directly use, let's say, the left division of A backslash of B, right? So the A basically are the different X and Y values, right? Or the H and F values, right? And then the B is the no the basically the matrix. Well, the A is going to be a bunch of one because those are the constants, right? And then the B are the values or the coefficients in front of the height. While the let's put it this way. Okay, it's easier if I type it out. Okay, so let's see another solution forced through zero. So we have to consider this problem into the way that A multiplied by X equals B, right? So then basically we're trying to solve what is the A here, okay? So if it's forced through zero, then what we do is we'll just put A value, which is 0, 1.7, 1.95, or just put A value to be H. Well, B is F, okay? Because eventually for this equation, if we expand it, I think it's not so clear if we represent in this way. So let's say that we have it as A multiplied A plus B multiplied by X. Okay, let's make it M. Right? L multiplied by X equals M. So we're trying to create a linear regression, right? So basically trying to find out what is the A and what is the B value for that can fit the X and Y value that we have in the system, right? So basically the X are the H, right? The Y is the flow, right? So we wanted to find out what is the A and B value. Okay, so because of that, if you want to, this is an over-defined problem because we have so many measurements, right? H, F. Theoretically, if the system is accurate, then you just need two equations, right? Because we have two unknowns, A and B, right? And then we just need to use two measurements to determine this linear relationship. But the thing is that the measurement is not accurate. This is an over-defined problem. And that's why we have to do measurements at multiple points, right? And then use the left division method, right? So the goal is to find out what is the A and B and what is a B, right? So then we have different measurements at different H values, right? So basically the matrix, right? So the matrix that we wrote over here is going to be one, let's say H1, right? 1, H2, 1, H3, right? So we have multiple equations, 1, 2, 3, 4, 5, 6, 7, 7 equations. So it's going to be 7 rows of these parameters, of these values, and then the F on the right-hand side, where F is basically the M, right? So now the thing is, we're forcing this equation to go through zero. So what it means is that we don't want this A anymore. We don't want this intercept anymore, right? If you don't want that intercept, then you should define the L to be directly the series of H. Okay, so it's going to be, right, B multiplied by H equal F, right? This is an overdefined problem again, right? So then what you do is you get basically slope is going to be H prime, because we have to make it a vertical matrix first, right? Left division of F prime, right, which is a transpose. So now we can see the slope. So this is our slope. Okay, so then we can do plot H nu and then slope measured by H nu. Right, and in terms of the legend, let's put it over here. Worst first order. Okay, so this is our new plot. So you can see that our new plot has this fitting. So you can see that our new plot actually has this fitting that goes through the 0, 0 point, right? So this is going to be a better fit compared to if we don't constrain what happens to the first order polynomial fit, okay, or the linear regression. Okay, so these are the different ways to fit the data point. Okay, the second example is trying to fit the heat capacity of certain gas, right? So the amount of energy necessary to warm a gas 1 degree Celsius depends not only on the gas, but also the temperature, right? So which is quite different from what we thought, because most of the time, let's say the heat capacity that we consider is going to be a constant, right? But then it turns out that if the temperature gets higher, the heat capacity of the gas also gets higher, which means that it can store more energy. So this relationship is commonly modeled by polynomials. For example, consider the data for carbon dioxide in this table. So it wants us to use MATLAB to model these data as a polynomial, then compare the results with those obtained from the model published by someone, right? So this is the model result. Okay, so then this is a higher order polynomial fit, right? So it wants us to use the, we could use a third order polynomial because we're trying to compare against this result here, right? So gas heat capacity here, you'll see, all right, so T, you see that the temperature is separated by 50 degree Kelvin, right? And then at the end, it starts to separate by 100 or 500. So we can define it as 250 separated by 50 until 800, right? And then 900, 1000, 1500. Okay, so this is how the temperature looks like. Now we need to type in the CP because we don't have the PDF here. Let's just type in everything. It's going to take some time. So 791. Okay, so these are our data sets. Okay, this is T and CP. So as we have done before, we should make the plot first. Okay, so we go here. So let's do T and CP. Okay, so this is how the data looks like, right? So as you can see, we can't really fit it by a linear line because you clearly see this curvature here. So it has to be either second order, for the third order, or even higher, maybe. Right, so then here it wants us to fit by a third order to compare the results here, right? So then what do? We actually do a first create this finer temperature, right? So it can be 250 to 1500, then separate by, let's say 10, okay? So it's much finer. So then CP new is going to be poly val, and then poly fit of T and CP, and we're talking about third order, and then putting in the T mu. Okay, so then hold on mu, and then CP mu. And then let's do the same thing. The legend, we create legend. So beta, third order. X label being temperature. Y label being CP. Kilojoule per kilogram Kelvin. Okay. So this is how it looks like. Right. So you have the data, you have the third order polynomial fit, and then we just need to find out the parameters. So to find out the parameters, we just do polyfit. Right? So provide the polyfit here. So then these are the results, but you can see that it also has a lot of zeros here, right? So the reason why it has zeros is because similar to here, right? So the parameter in front of the t to the power 3 is going to be really, really small, right? So it's only going to show you the first 4 of the values, right? So you can find out these values from the answer here, right? So if you double click, right, so you can see these values. So you can see that actually I would say they are pretty close to each other, right? Although they're not exactly the same, depends on what type of fitting you're trying to do. Of course, by this time, right, this author probably don't have access to MATLAB to model the data, right? So then they're a little bit different compared to each other. Okay. So I mean, we were showing that as the answer, but you can also just pass these to a parameter, for example, fit, right? So then the value are actually saved in this matrix or in this array, which is a fit. Okay, so then you can compare the values here. They're not exactly the same. Okay, so we have been showing these codes to conduct the fitting, right? Actually, in MATLAB, there are tools for us to directly do the fitting, right? So basically, these are useful when we are trying to directly get a feeling of the data. Let's say we're getting the curve fitting being more interactive, right? And especially when we are not trying to directly get the results from the coding. Okay, so what I mean is that basically we can start a new section, right? So let's talk about the heat capacity. Right, so we're trying to do the interactive, right? So this is the result. Okay, let's see, where's my plot? Okay, so this is our plot. All right, so this is the basically the result of the data, right? So to do the fitting, we can go to tools and then basic fitting. So you're going to see a panel showing up on the right-hand side. So this is data, right? We already have this label here. You can use different types of fitting. So you can, for example, show linear, right? And then basically this is the equation. You see that linear fit is not a really good fit. Quadratic, getting better. Cubic, even better, right? So we're trying to fit the data with a cubic fit. So now let's just uncheck the other one. This is a cubic fit. And then this is the equation. And if you recall, earlier we showed that the value are going to be it's going to be in this range. So actually it's exactly the same value. So we just run this function again. So you can see the fit is over here. So let's just copy these data here. Fit 2.7. Let's just temporarily memorize this. 2.7 e to the minus 10, 1.06 e to the minus 6, right? So that, well, yeah, we could actually directly show the data here, right? So this is the data. So yeah, we're trying to fit the data here, and this is how it looks like, right? It's exactly the same coefficients that we obtained from the third order curve fitting. It has to be the same because using the same algorithm, right? So you can also show the R square, right? 0.9999, norm of the residues. So actually an interesting feature for this curve fitting is, for this interactive tool, is that you could also show the error, right? So basically you can show that as a bar error. So this shows you the residues, which is basically the difference between the data and the line. Okay, so basically here is the third order polynomial. You can also show the linear, right? If you see the linear, you can see the residue at this lowest temperature, 250 degree Kelvin, right? It's the biggest, and also the biggest over here, right? So basically the lines are over the data, so that's why you have negative residues. And then, but over here you have positive residues, right? So there's a more direct way to visually show the residue or the error from your curve fitting and the data points. Okay, but if you see the third order polynomial, right? So the error is much smaller by comparing, let's say, the linear fit, which is a yellow color, and then the green fit, which is, the cubic fit, which is in green color, right? So you could also fit it with different different orders, right? Even higher orders, fourth order, fifth order. Let's say we um, remove the, let's say, the linear fit, right? So you can see this is the third order, fifth order, fourth order. We can try fifth order, and then fifth order. This is the equation over here. So let's not show the equation. Let's not show all of these equations. And then we can try even higher order, let's say ninth order, right? Ninth order. It looks like they still fit pretty well. Right. 10th order, right? If you, yeah, basically they can, but now if you see this, let's say the 10th order line here, right? It start to have this very weird spike, right? Again, this is an overfitting problem because by reducing the error, you're introducing much more uncertainty to the coefficients, right? So you could have a spike that goes really high up and doesn't make sense. Right? So that's why we don't want to do overfitting for our data. I would say here that we can, I think it's okay for us to just use the third order. Okay, it already give you very good or very small errors. Okay, so this is the example of how we can do linear fitting, right, with the interactive tool in the plots, right? So we could also basically set up the curve fitting tool, right, which is the interactive curve fitting tool by just typing CF tool. Okay, so a window is going to pop out. Okay, so yeah, it's being shown over here, right? So then to do the curve fitting, what we need to do is first to select the data, right? So you can select the data based on what is already in your workspace. So you can do X data to be X to be temperature, and Y data to be CP. Okay, so you can see that there's already a line showing up. But the thing is that we're trying to use a polynomial fit, right? So polynomial fit, then we're trying to do third order polynomial fit. You directly see the fit of the result, right? So this is again the data. And then it also shows you the confidence level, right? So what should be the range of this coefficient, right? In terms of the third order parameter, right? And then over here, and then the goodness of the fit, right? R square value, RMC, and root mean square error, right? So give you all the different parameters. So I would say that the advantage for the interactive curve fitting tool compared to the plot that we showed earlier is that if you pay attention for the plot method, Let's just create a plot. Okay. So for the plot method, when you do curve fitting, that's why it's called basic fitting, right? So when you do fitting, you can only do polynomial over here, right? First order, let's say linear, quadratic, cubic, so on and so forth, ninth order, 10th order. So it's only polynomial fit. But a lot of times our fit could be different, right? So here is showing you the polynomial, but then there could be, let's say, reaction that's having this exponential decay, right? So we're talking about the organic concentration having exponential decay, or the Gaussian distribution. Let's say we're talking about the, let's say, the score, right, of, for example, let's say we're trying to measure the length or the size of the particle that's suspended in the air, right, or size of the suspended particle that's in the water, right? So they're going to follow the Gaussian distribution. Okay, so one example can be, let's say, we're trying to have, let's say, the particle dp diameter, right, being 1 micron, 2 micron, 3, 4, 5, right? And then the length or number of particles in each size can be, let's say here it's 3, 20, 100, 19, right, and 2. So now if you plot dp and n, right, so let's try to copy these to our code over here. So this is Gaussian fit. Okay. This is how the plot looks like, right? So you see that, well, basically we're trying to measure the number of particles or number of suspended particles in each size beam, right? 1 micrometer, 2 micrometer, around, let's say, between 0.5 and 1.5, and 0.5, 2.5, so on and so forth, right? So this is our distribution. So we know that it's going to follow a Gaussian distribution because this is how the nature looks like, right? So now if you do the basic fitting here, there's no way you can do the fitting, right? Because this is, everything is linear. Okay, although you could do, let's say, ninth order polynomial, but it's not going to give you the actual, right, the actual Gaussian distribution, because Gaussian distribution is dependent on exponential, right? So then what we do is we'll actually use the CF tool and then put in the particle size, dp, y data being n, right? So this is, right now the default is polynomial, but then we can use Gaussian, right? So you can see the Gaussian distribution almost perfectly match what we're expecting, right? The Gaussian distribution will further give you the prefactor, right? So it's basically represented as A1 exponential x minus b to divide by c squared, right? So B1, we know this is the average, right? And then this is standard deviation. This is a prefactor. Okay, so the B1 is average, right? You can see that it's close to 3, which makes sense because at 3, we have the highest concentration. This is the average size, the mean size of all of these, let's say, the suspended particles, right? So this is the Gaussian distribution. But there's actually a problem with the Gaussian distribution, or what we call the normal distribution. The thing is that if you follow this equation here, what you can see is that even when the particle size is negative, you still have certain number, right? Let's say the particle size is minus 10 micron, right? But the equation doesn't care. It will always give you a concentration or a number here. So that's why people also use the log normal distribution to represent certain size distribution. And due to the time limit, I will not show this anymore. So basically the log normal distribution is, instead of using dp, we use log dp, right? And then calculate the normal distribution. So what it means is that, so we will calculate log dp being log of dp. Okay, so we'll make the plot. It's log. Okay, then not here. So we do CF tool, Gaussian distribution, select data. So x will be log dp, y will be n. Okay, so instead of using the normal distribution, right? So now if you have the log dp, so you can see that basically even when you have x value that is negative, it simply means the log dp is negative, right? The natural log of dp is negative, which means that the dp can be still positive, right? Because the log of, let's say, anything below 1 is negative, right? So even you fit it with a log normal distribution, note the x-axis now becomes log dp, right? So log dp of 0, which means that it means that only the size of the particle is 1 micron, okay? So now the x-axis will start to make sense. And you can see that if you fit it with a log normal distribution, then the mean size also gets shifted, right? So now it's a geometric mean size, and then it's at the a value of 1.073. So what that means is that the geometric mean is exponential of 1.073. 0.037, right? The geometric mean size is 2.82. Okay, so this is normal distribution, log normal distribution, right? So of course you can also fit it with power distribution, sum of sine, and so on and so forth. So the CF tool will give you more flexibility when you're trying to fit with different types of the curves. Okay, so that's it for the curve fitting, right? So basically, I want to use the rest of the time to talk about how we can solve equations, because in engineering, equation solving is the most important. A lot of times you may face very sophisticated equations, right? So it can be linear, nonlinear, explicit, implicit. Right? You might have heard of these terms before, but we're going to talk about their definitions. Okay, so solving equations normally involves or can be simplified as a function of x equals 0, right? Say we're setting f of x equals 0. Or if there are multiple parameters, right, it could be f x y equals 0, right? So we're going to face problems like these. Okay, so then the problem is, well, if it's f x equals 0, x is just a single parameter, so then this is a single equation, right? So if it involves x, y, or z, or so on and so forth, then this is a system of equation, right? We should also note that to solve a system of equation, if you have n number of unknowns, you have to have at least more than n equations, okay? So if it's exactly n equations, then n unknown n equation, you can directly solve it. But if you have more than n equations, then as we said, it's going to be an overdefined problem, and MATLAB is going to use the least squares method to solve the equation. Okay, so now let's start from the single equation, right? So then single equation is just fx equals 0, right? So we sort of introduce these three different methods: f0, fsolve, and symbolic mathematics. Okay, so let's so f0 we introduced that. Basically f0 and fsolve, we talked about these functions when we were introducing user-defined functions, where we have to create the function handles, right? So after we define the function, we can use a function handle to call the function and then further find out the solution. And here, pay attention that we're talking about a single equation, right? In symbolic mathematics, we can define the symbol and then use the solve function to solve for this equation. Okay, so the issues regarding solving the equations, or these especially single equations, there could be multiple roots, right? Like polynomial equation. If you have third order, then there could be 3 roots, right? So then the solution for this issue is to make the plot first to find out your appropriate root. Okay, so this is an example. So let's say that we're trying to solve for x squared plus sine x equals 5, right? So we know that x squared equals 5, then x is just square root of 5. And then now you have a sine x. So we cannot really solve this equation by hand, right? It's going to be very difficult. There's no way it has an analytical solution. Okay, so now let's go through these 3 different methods, F0, Fsolve, and symbolic mathematics. So first, F0. Okay, so if we want to do it in F0, we said that we could define a function. Just delete these pre-existing functions. You could define a function that basically has a form of x squared plus sine x minus 5. So y equals function 1 of x. And then basically y equals x to the power of 2 plus sine of x minus 5. Okay, so we're trying to call the f0 to make y to 0. So let's save this function, f1, right? So then solve single equation. Okay, so you can do fsolve. Let's say solution f0. And then let's say we use a function handle. And then we need to provide the initial guess, right? What is the initial guess? We do 2, right? Because we know that the square root of 5 is close to 2, and then there should be a solution nearby 2. Okay, so then we can run it. This is a solution, right? Solution is 2.025 something. So let's also clear and CLC. Okay, so these are our solution, 2.02. But the thing is that, well, it looks like there should be a negative root as well, because x squared will make it positive, right? If you have a negative of x value for the sine, right? So then it could also have a root over there, right? Or maybe it could be even more than 2 roots, because now we know the sine x function is circle, right? So it could be adding up and then create another root, or even more than 3 roots. So then the thing is, how do we know this, right? How do we know how many roots should we be looking at? So that's why when we were solving for these single equations, it would be the best if we make the plot first, right? So the issue is there could be multiple roots. So to test it out, let's say instead of using an initial guess of -2, we can use initial guess of -2. So if you run this again, you can see that the solution is -2.38, right? So it definitely means that there's another root. So then how do we know that, right? So we could use the easy plot, which is function 1. It's called the function, right? Easy plot x is function handle, and then this is the function, right? Function 1, and this is how it looks like. So x, this is in the range of -6 to 6. Remember, we said that if you use the easy plot, normally it's in the range of around -6 to +6, but you can also change the range if you're, let's say, concerned that there may be more roots. Then you can define the range for the plot. Okay, so now it's from -100 to 100, and you can see basically there should be 2 roots just based on the plot, right? So because it has a U shape. And then if you further look here, there will be a root over here, and there will be a root over here, right? So which means that now you know that there are 2 roots, and then you can use the initial guess accordingly to find out the roots for this single equation. Okay, so this is how we can use F0. So Fsolve is the same thing. Okay, you can run it, right? So Fsolve will give you the same result, right? So the only difference between F0 and Fsolve is that the F0, this function has to go across the x-axis. If it doesn't, then it cannot find the solution. So for example, F0, and then instead of defining F1 to be this function, let's make it to be x squared, right? X squared is a parabolic function. we know that the root for this function is 0, right? So if you use f0 and then even give it an initial guess of 0, or let's say 0.1, okay, it's going to give you that the solution is not a number, right? But if you use fsolve, it's going to give you the solution. It's close to 0. Okay, so although it's not exactly 0 because fsolve is using the iteration method. It's an iteration, and then there's an error range for you to set up the termination of the iteration. Okay, so it's close to 0 basically. Okay, so it's this is the difference, right? So f0 and fsolve. So that's why when you're trying to look for the root of a single equation, we should be using fsolve. Okay, so then basically people may also complain that, well, to solve for this equation, you have to define a function. Isn't that too cumbersome, right? So actually, there's an easy way for us to bypass this, right? And so instead of defining a function in a separate M file, like I mentioned here, right? So you could use M file function. You could also define an inline function. So we simply covered this in our, briefly covered this in our user-defined function chapter. So how do we do that? So instead of defining this function as an M file, you could just define function 1 being in this way. Okay, so now instead of calling the function handle, because here you already created the function handle, you can directly use F1, the function name, and then do all of these calculations, right? So this is an inline function way to sort of define our function, right? To further basically do the calculation. Okay, so if you run this, it's the same thing, equation solved. Okay, so this is by using the inline function. So in this way, we don't need to define a new function. For example, you can also change it to function 2 or any name, right? So then this is your solution. And then we'll also make the plot by using the easy plot. Okay. So this is an application, right? So for example, we're talking about the particle drag or an object drag, right? So then there's a drag coefficient. Here is the C3 term. So there are different drag coefficient forms. So it turns out that through the calculation, you find out that the drag coefficient is 10. And then what is Reynolds number? Okay, so then this is a single equation, right? So there's really no way for us to solve the Reynolds number analytically based on the function, right? So then solve single equation Reynolds number, right? So then we can define, let's say here, CLC, this function, let's do function 1 equals at x, 24 divided by x, multiplied by 1 plus 0.15 x to the power of 0.687. Okay, and then we said that it has a value of 10, so minus 10. And then let's do easy plot function 1. Reynolds number has to be larger than 0, right? So let's make it 0 to 20. Okay, and let's solve. Function 1. Let's give it a starting point of 10. Okay. Oh, let's see. All right. So then you see that this is how the function looks like. It actually goes across 0 here, right? So we can basically guess that the Reynolds number is going to be close to this value. Okay, so then we can give it an initial guess, right? So it looks like we have to define a function handle here. Let's see. Undefined function fsolve, or should be fsolve, SOLVE. Okay. All right. Okay, so this is solution 3.2. Okay, right. So we'll see, basically you can use fsolve. You can also use f0, right? Get the same thing because it indeed go across the x-axis. Okay, so these are the two methods, right? F0 and solve. And you could also do the symbolic calculation. So the symbolic way is just to have S sim Reynolds number, right? Sims Reynolds number, and then basically function equals let's see, 24 divided by Reynolds number multiplied by this whole thing. Right. So then for the symbolic mathematics, then you can directly use solve fun. Okay, so if you want, you can also do easy plot of fun, right? It's the same thing. If you run it, right? So this is the solution. Okay. See, solution are parameterized by the symbol Z2 to include parameters condition. The solution specify the return conditions. Let's see. I think we can also, maybe it's related to the dot calculation here. Sims Reynolds number. Let's try again. Okay, dot divide. Okay, so this is not our solution. So instead of changing it to using Reynolds number, let's use X. Okay, we can hide these first. Function. Okay. Well, it should be returning us a value, right? Let's see. Or maybe let's try this function first, right? So try this equation. Okay, it could be that for more sophisticated functions, they cannot have a solution, but this is very strange. So let's see, define a new name. Let's see, function 3. It could be that it's calling some of the functions that we didn't see. Yeah. Since x. Okay, let's try another function. So x to the power of 2. Try this one. Okay, it is giving you a value. So it looks like it could be there's something wrong with this equation. So maybe for more sophisticated equations, we cannot really use the symbolic mathematics. But you can see that, well, basically we can use the other F0, Fsolve to solve for these problems. Okay. So then the next example is the solving for the system of equations, right? The system of equations, then we can further divide these system of equations into different scenarios, right? So there could be scenario that you have a set of linear equations, right? So we said that linear equations can be represented as a matrix multiplied by x equals b. We talk about this in linear algebra and also the regression, right? The linear regression. So we said that the method we can use first is the inverse method, x equals a inverse multiplied by b. But the thing is that this requires A to be a square matrix, which means that you cannot solve for underdefined or overdefined problems, right? So under that situation, we have to use the left division method, okay? So you can directly find the solution, right? And then we could also use the fsolve function to create the functions in a MATLAB file and then further solve it. or use the symbolic mathematics. Okay, so this is talking about the linear equations. So we could also define, what about nonlinear equation? Nonlinear equation, we can only use the f-solve or symbolic mathematics. So what I mean is that, for example, we talked about this mass balance problem. It's talking about desalination unit. You have the input of flow that has water and salt that is separated into pure water on the top branch, and then sort of the salty water in the lower branch. And we set up the mass balance of water equals the water from the top and then the water from the bottom, right? And the mass balance for the salt is the salt from the top, from the total, the inlet equals the salt from the top, which is 0, and then the salt from the salty water, okay? So then you could define, say, system linear equations, right? So you could define A as being 1.9, then 0.1, right? And B being 96 and 4, right? So the solution x is just A to the power of -1 multiplied by B, right? So this is the inverse method, okay? So you could also do left division B, right? So these are the methods. So you could, as we said, you could convert, and we already talked about these two. You could use the f-solve function. So basically define function, let's say y equals, let's define define 10 of x. So y1, which is the first equation, being x1, now make m top being 1 and m bottom being x2, right? So m1, x1 plus 0.9 multiplied by x2, and then minus 96. Y2 being 1 multiplied by x2 minus 4. Okay, so these are our two equations. Okay, we have to define this function, and then solution being solved at function 10, and then we need to give it an initial guess. So make it 10 and 10, right? So this is the solution, x1 and x2. I think we could also use the f0. Let's see. No, f0, only single parameter, right? Only single unknown. So then f-solve can basically give you the right answer. You could also do symbolic mathematics, right? So sims x, x1, x2, right? So function 1, I think we have defined so many function 1s. Let's do f1. Let's say function 1, right? Let's copy some of the things here so it can save us some efforts. X1, X2, X2, function 2. Okay, so then it's solve function 1 and function 2. Okay, so then it's going to give you x1 being 60, x2 being 40. Right, so these are the different ways to solve for linear equations. What about nonlinear equation? Right, so then we're going to talk about this. Like this one, you can also use these methods we talked about. So nonlinear equation also involves the implicit equation. So now we need to talk about what does it mean by implicit, what is explicit. Right? So explicit equation are basically the dependent variables is isolated on one side of the equation. For example, y equal fx, right? So if you have any x value, you can find out what's the y value. That's explicit. Implicit equation can only be written in this way, fxy equals c. So basically, you cannot isolate the parameter from one and the other, right? So then this is going to give you some trouble when you're trying to find out the solution. So for example, this is a set of implicit equation, right? So x squared plus y minus 5 equals 0. Exponential of x plus y squared minus 8 is 0. So you see this, the parameters are dependent to each other. and you cannot really isolate one from another, right? So then the issue or how we can solve this problem, of course, we cannot convert it into linear equation anymore, right? Because these are nonlinear. So the solution that we can use are going to be F-solve and symbolic mathematics. So we define this F10 again. So the function, now we have, what we need to do is we need to convert x and y to x1 and y1. Okay, so then what it means is that we convert this to, or x1 and x2. Okay, so x2 minus 5. Right, so x into x1 and then y into x2. So then it's going to be exponential of x1 plus x2 to the power of 2 minus 8. Okay, so just for to avoid problems, let's use a dot calculation here. So you have y1 and y2. So now the problem is to basically use f-solve to make y being 0. Okay, so then you can do f-solve or solve, f-solve. Let's do the same thing. Let's put the same values here. Then we could also hide these terms. Okay, so this is a solution, right? So yeah, this is going to be what we want from this calculation here. Okay, so you could also use the symbolic calculation. So what that means is x1 and y1, we already defined it here. So let's just copy the functions that we want. So it's going to be x1, x2, x1, x2. And then directly use solve to find out the solution. Okay, so these are the two solutions. It's going to be, let me see, are they the same? Actually, they're a little bit different, right? So you can see there's a positive term and negative term. So that's why for these explicit or implicit calculations, they also have the problem of the multiple roots, right? So then I think under that situation, we'll probably need to make the plots again, right? So to find out the accurate solution um, for our equations. Right? So for example, let's try to give it a similar initial guess. Then you can see that these two give you exactly the same answer. But then, you know, for these higher order or nonlinear equations, they could also have multiple roots, right? So then they could be different. And the problem for the solve function or the symbolic mathematics is that it doesn't give you like multiple roots, right? So under that situation, I think we still need to make the plots. So how do we make the plots? We can just do y equals x squared, 5 minus x squared, and then y equals square root of exponential x, right? So basically, since x and then y being, let's say y1 being 5 minus x to the power of 2, y2 being, say, 8 minus exponential x to the power of 5. Okay, so easy plot of x on y1, hold on, easy plot of y2. Okay, so you can see that basically there are two solutions, right? So then we can do, make it bigger, minus 5 to positive 5. right? So there is a basically an intercept over here, right? So then there's also an let's see, we'll find the solution, x and y. Yeah, because it's also limited by the y range. I think a better way is to make the plot that shows a wider range of the y value. Okay, so then for that, I think we can do a, basically you see x1. This is one root, right? So minus 4 point something, and then the other root is x equals 1.8, which is close to 2, right? And y is 0.9. It's probably somewhere here. And although it's not very close to each other. Okay. So under this situation, I think it's also limited by the error of the f-solve function. Okay, so it turns out that this is more sophisticated than we thought. But you can see that basically these are the ways that for us to use the f-solve function to find out the roots, right? But still, it's always safer to make the plots first and then find out the solution. Okay, so that's it for this class. So this class, we talked about curve fitting with higher orders of polynomials. We talked about the curve fitting tools, and then we specifically introduced the ways to solve equations, right? It can be single equation or systems of equations. There are different ways for us to use when we're facing like higher order, more sophisticated equations and trying to find the roots. Okay, so that's it for this class. Let me know if you have any questions. Thank you.